then you will certainly need a kind of Dedekind axiom to ensure you are really working over the real numbers. Okay. What kind of axioms do you have? Well, there are in this chapter 5, I think, in Stillwell, any given two distinct points, there is a unique line passing through them. And dually, given two distinct lines, there is a unique point they have in common. Yeah? And an axiom like, there are 3 points which do not lie on a line, which just ensures us that the geometry is not one-dimensional, but at least two-dimensional. Axioms like that. Okay, we didn't look at that. We did talk about axioms in hyperbolic geometry. Yeah, because hyperbolic geometry, what's the most important property of hyperbolic geometry? Well, it satisfies all axioms in Stillwell. I mean, these Hilbert axioms, page 43 or something, including A and D and E, the 3 fancy axioms, except, of course, the parallel axiom, I4, the Playfair axiom. Okay. But that's partially, it's mainly a positive statement. It satisfies, how many axioms are there? 4 plus 6 plus 4 makes 14. 4 plus 6 plus 4, 14, 15, 16, 17, 16, I think. It does satisfy 16 out of 17 axioms, but not I4. Okay. But, and that I think was Amos' question, maybe it satisfies another axiom, kind of replacement for I4, and that's true. Okay. I should maybe draw a little picture. So we have Euclidean geometry, let's say real. So I mean R2. Yeah? And we have real hyperbolic geometry. Yeah? Okay. And what do they have in common? Well, they satisfy these 16, I think, axioms. So all axioms except I4. So that's something which they have in common. That's not something which distinguishes them. That's called neutral geometry. So that means axioms I1, I3, B1, B4, C1, C6, E, A, and D. But not I4. Not the Playfair axiom. Okay, but now I'm not denying the truth of the Playfair axiom. I'm just ignorant, agnostic. Okay? I don't assume anything about the parallel axiom. It could be true, it could be false. I don't care at this point. That's called neutral geometry. And so this is a type of neutral geometry, and this is another type of neutral geometry. And there is a theorem by Sakeri, which I mentioned last week, and Desargues and other people, which in fact tell you that these are the only 2 types. If you have all these axioms, there are only 2 types. Either you have, it's almost true what I was saying now. Either you have this, or you have this. It's almost true. Okay. Now, yeah, because Desargues and Sakeri, they did assume, and now I'm coming to your question, they did assume, so suppose the Playfair axiom is wrong. They were not doing neutral geometry, as Euclid is. The first 28 propositions in Euclid are neutral geometry. Yeah? You don't use the parallel axiom, and you don't replace it by another axiom. What Sakeri and Desargues did, and I didn't tell you, but they replaced the Playfair axiom by a different axiom, which is called kind of the existence of asymptotic parallels. So he assumes, so here we add the Playfair axiom, and here we add an axiom about asymptotic parallels. This is not part of the exam, of course. So what he assumes is this: in this playfair situation, you have a line and a point not lying on the line. So suppose we know there always is a parallel line. That's a conclusion of exterior angle theory. You always have at least one parallel line, exterior angle theory, in neutral geometry. And now I'm going to rotate this line through this point. And then in hyperbolic geometry, there are more lines which do not intersect. And he assumes that there is a kind of limiting parallel, which is the last parallel which does not intersect. But if you rotate even further, then you get an intersection point. And he assumes there is one such asymptotic parallel on each side. So that's the hyperbolic parallel axiom, Legendre and Sapir assume. And then you can show, if you have all these axioms, including this parallel axiom, the asymptotic parallel axiom, then you get the hyperbolic plane theory. That's the only example. So if you have all these axioms, then R2 is the only example. If you have these axioms and this axiom, then the model we were looking at is the only possible geometry. So that's for the example.
And my question turns out to be very difficult, but it actually was something that the difference between neutral geometry and real Euclidean, that was the missing link between the two for me.
Yeah.
And I thought that the projective geometry was the one linking them, but that isn't, I think.
Yeah.
And then I forgot about the exterior angle theorem, that there always is at least one parallel line. So that's why I didn't know what the negation of the denial of I4 was.
So in neutral geometry, you do not deny, you do neither assume the parallel axiom nor do you deny it. You don't say anything about it. Here you really deny it in a certain way.
And the denial sort of is there are possibly more than one parallel line.
Yeah, but it's a bit stronger. It's this, and there exist two asymptotic parallels. So it's kind of continuity thing. Okay, your question about Emil, about how does hyperbolic geometry fit into this hierarchy? Okay. Well, I wrote a document this morning and I show it to you on Blackboard.
Don't you use the moment section?
It's called holography. Most certainly not. Don't read it.
At home.
Zu Risiken und Nebenwirkungen lesen Sie die Packungsbeilagen und fragen Sie Ihren Arzt oder Apotheker. So, okay, so
That's the answer.
I'm a trained professional. I will open the document.
Would you please put the camera?
So don't worry if you don't understand. So now this is your question. Yeah? Does the hyperbolic plane fit into this picture? Above this here I described this hierarchy we know. Yeah? Euclidean similarity F1 projective. Okay. This is just what we all know.
Minus number 2.
Because everything's two-dimensional.
Yes.
Yep. So the answer is yes. The question is hyperbolic geometry a specialization of projective geometry analogous to the way Euclidean geometry is a specialization of projective geometry? It's an excellent question. And the answer is yes. And it's really beautiful. So this is the projective plane. If we choose a line, we get affine geometry. Yeah? If we fix the line, we get affine geometry. Okay. How do we get hyperbolic geometry? By fixing a conic. So we take an interesting conic. And now we look at all projective transformations which fix this conic. Not point-wise, but as a set, as a conic. Okay. And the group you get is the group of hyperbolic isometries, the Möbius transformations. And so in the point of view of Felix Klein, that's already a definition of hyperbolic geometry, because you don't need the plane itself, you only need the isometries. But maybe we would like to see the plane itself, and the points and the lines and the angles and the line segments. Well, any idea what the points of the hyperbolic geometry are here? Well, the interior points. This is just the point of radius on the upper half plane. It's the same thing. Projective geometry. Okay. And last time we've seen, and what are the lines? Well, this is not the Poincaré model with the circles. This is the Beltrami-Klein model. It's a different model of hyperbolic geometry. They're all isomorphic. You could look at it as kind of, if you take the Earth and you take an atlas, you have different projections which have different kinds of distortions, but it's all pictures of the same Earth. It's different representations of the same thing. It's the same here. So you get a different model of the same hyperbolic plane. There is only one if you have sufficiently many axioms. It's just intersection. You take a projective line and you take the part here. That's the Beltrami-Klein model. Well, these are, of course, preserved by projective transformations. So that's a good thing. And the projective transformation maps lines at infinity, points on the boundary to points on the boundary. You can define the notion of distance using cross ratio, of course, and so on. So the answer to your question is yes. Thank you for your question, because I was forced to think about it this morning. And so I noticed this, which I really like. Oh yeah, what I just said, affine geometry is projective plane plus the choice of a line. Hyperbolic geometry is a projective plane plus the choice of an interesting conic. And then last week we talked about holography, remember? The hyperbolic isometries of the hyperbolic plane of the interior is the same as the projective transformations of the boundary. Yeah? And that's okay. And okay. Last week we thought that the boundary is a line, projective line. Now we understand that it's really a conic, but there are isomorphic, so that's why we couldn't see the difference. So everything is connected, but this is Higgs draconius. This is not the inside. And then there is also a beautiful connection with general relativity or special relativity. This is not for the exam.
Make it a bonus question.
So we know that the real projective line is the boundary of the hyperbolic plane, and not just as a subset, but even in the sense of Felix Klein, they have the same transformations. This boundary has the same transformations as the hyperbolic plane itself, and the hyperbolic plane itself lies in Minkowski space. Nice thing. You get 2 plus 1 dimensional Minkowski space. In physics, people are more interested in 3 plus 1 dimensional Minkowski space, because it looks like we have 3 space dimensions. And in 3 plus 1 dimensional Minkowski space, we have the 3-dimensional hyperbolic space, which has a boundary, which is topologically a sphere, of course, and the sphere is the projective line over the complex numbers. So the thing we know, I learned from Stillwell, that the boundary of the hyperbolic plane is the projective line in the sense of Felix Klein. Same transformations. The similar thing is true 1 dimension higher, but you have to take the projective line of the complex numbers. So you get a complex plane plus 1 point at infinity makes a sphere, the Riemann sphere. It's the boundary of 3-dimensional hyperbolic space, and this lies in Minkowski space, 3 plus 1, and these 3 spaces, this is 2-dimensional, this is 3-dimensional, this is 4-dimensional, they all have the same transformations. So in the sense of Felix Klein, special relativity is just a geometry of the projective complex line. Funny, isn't it? So